Okay, so welcome everyone. Good morning. Sorry for the delay due to technical problems, human problems. So we are here today for the 13th seminar in this series of the SMAC Talks, short seminars on astrophysics. Please mute your microphones unless you're speaking or you wish to speak, and keep your cameras off. Today the speakers are Vicente and Mohammad Akhlaghi, and they're going to tell us about containers and the talks in two parts for two types of containers, for Docker and Singularity. So welcome, Mohammad. Please go ahead.
Okay, yes, thank you, Carlos. I hope everybody can hear me okay. I'm going to share the screen. And yeah, so now this should be I hope you can all see the slides. So as Carlos was saying, the idea of today's talk was just to give a brief introduction to containers. Mainly Docker and Singularity are the most popular ones. So probably most of you have heard about what containers are. Maybe it's not very clear, the distinction perhaps with a VirtualBox or virtual machines, which is also very popular. So the idea of today was just to give an introduction to containers, explain the difference with virtual machines, etc., and then give some actual use cases and some examples of how to use both technologies, Docker and Singularity. So the structure of the talk is very basic, so I will explain first the basics of containers, then Mohammad will give the intro to Docker, and then later I will give the intro to Singularity. I put there because the name has basically changed. Now it's called Apptainer. If you look for Singularity, there will be still many links in the web, but the name change happened just about 9 days ago. So now it's called Apptainer. So then for container basics, we basically have that a container is just a standard unit of software where you will package up code and dependencies, okay? So the idea is that many times you maybe need to have in one bunch just a particular piece of software with a lot of libraries, etc., and that sometimes is actually very difficult, or at least a lot of work to actually move from one computer to another. So the idea of a container is that you can put all of it together, and then when you move to another computer, it doesn't matter which distribution you have, or it will run with the pre-installed software and all the pre-installed dependencies. So it's much easier to move the code from one computer to another. As for terminology, we'll go through this quickly, but basically there are some different terms that sometimes you can get tripped over. So probably you heard about QEMU. So for example, this is emulation. This is a different technology. This is the sort of stuff you need if, for example, you feel nostalgic and you want to play your Spectrum games. You will need to emulate the processor that an old computer had. Wine is also something different. This is a portability layer, so you can, in Linux, you can run some Windows programs. But the main ones that you probably heard, and there is some confusion over the terms, is virtual machines and containers. A typical example of a virtual machine is the software VirtualBox that I guess many of you have used already. And then containers, actually, there are many different technologies. We have Docker, Singularity. Those are the ones that we are going to talk here. But there is also Podman, Saru, Sifter, and many others, okay? The main difference between virtual machines and containers probably can be seen here in the figure. So on your left here, you have machine virtualization, and on the right, you have containers, okay? So, well, virtualization can be done via hardware or also software, assuming that we are doing it with software like VirtualBox. So the idea is that you're going to have a piece of software like VirtualBox here, And then on top, you can install a complete operating system. Okay, so in case of assuming that I'm running Linux, I can install, for example, a different Linux system, and then I will install the whole operating system and then all the libraries and applications that I want. But then this is the important part. Okay, I have to install the whole operating system, which basically means, at least for this talk, I have to install at a minimum the kernel. And with this, I can install different operating systems. So for example, this one could be a Linux system, this could be a Windows system, etc. Containers are different because the only thing, you skip this part, you skip the guest operating system. So you are running, for example, in my case, I'm running Linux with a particular kernel, and you will only install the libraries and the application. So all of them are running the same kernel. Okay, so the kernel, in case you don't know, is just the part, the most basic, closer to the hardware part of the operating system, the one that is actually taking care of communicating with all the actual hardware of your PC. Okay, so if you don't have that, basically when this application needs to, for example, write to a file, you will actually use the kernel of your host operating system. That means that you cannot have, for example, if I'm running Linux, I cannot install Windows, but the advantage is that it doesn't have to do this sort of translation from one kernel to the other, and it will be much faster. Okay, so it has the limitation that you will not be able to run as many operating systems as with a virtual machine, but the advantage is that it's much more lightweight. So it's much, and you get much better performance out of your applications. So containers basically are good, for example, as what I said, if you want to bundle some software and dependencies in a single portable package that you want to move across computers. Also for reproducibility. So if you want to get a paper with some data and you want to make sure that you have exactly the same libraries and you're going to always get the same results, so you can package all in one bundle, and it doesn't matter if you update your system, you can run that container to get exactly the same results. And for example, something that I use quite often as well, to test software with different Linux distributions to make sure that your software will run with different libraries, etc. And as just a few notes, so yeah, as I said before, the startup and performance compared to virtual machines will be much better. But for example, if because you share the kernel with the host operating system, so if you need something a bit special and you need to try to study, for example, kernel variations, you will not be able to use containers. So if you want to run, for example, Windows on top of Linux, then containers is not a good choice. Okay, and in some scenarios, actually, a virtual machine is easier to set up. If you are not too concerned about performance for certain applications, for example, like graphical applications, so if you have a complex setting, like you have to redirect many ports, etc., then maybe it's easier to use a virtual machine. Okay, and just a note, in case you use, for example, virtual machine, there is also a package called Vagrant that it will help to set up virtual machines very quickly. But if you need this, if you are not in this sort of list, containers can be extremely helpful. Okay, and so just to see what is a normal usage workflow of containers, this is basically done for Docker, but the ideas for Singularity will be similar. So you have an image that is a file that contains the applications and all its dependencies. Okay, so for example, here we are assuming that we have this Docker host. This could be my machine, and an image. I will have a list of images here. This could be, for example, an Ubuntu. This could be Engine's image, and so these are files basically that are stored in my machine. Then the Docker file, or we can call it in a different way, but basically to create these images, you need a file that is like a recipe that will build the image. Okay, so you will specify what software you want to install, what is the base distribution that you want to have, etc. And then using that Docker file or Singularity file for Singularity, then you will create something like this. And then a container, this is an important difference, is an instantiation of an image. Okay, so for example, here I trust that you can see the different lines. When you have Docker build, for example, basically you will you will create a particular image. When you say Docker pull, for example, you actually go to a registry, which is basically just a place somewhere on the web where there are images, and you can get the image from the registry and download it to your machine. And then the important thing, when you do Docker run, that one will actually use one of the pre-existing images and will create a container. So a container is basically an instantiation of one of these images where you can run things and you can actually modify these things. You can create files, you can do whatever you want, like with a normal operating system, but the image itself is not modified. Okay, so actually out of one image you can create different containers, and each of them lives separately. They are containerized, obviously. The purpose of this, at least for Docker, is isolation. So each of them will be different entities, and you can later destroy them as you wish. But that's the idea. You have a registry where you have a database of images. You can download into your machine, and then out of them you can create containers to run your particular application. So then this is the last slide before we go to actual examples. So the idea is that the images are immutable. So they are basically built out of read-only layers. So you can take an image from somebody else that has, for example, imagine this is the layer of a base Ubuntu system. On top of that, you can add some libraries. On top of that, you can add some application, etc. And then out of that, you create an image file. And then from the image file, you can create the container. And then the container will have a read-write layer. So you can interact with the container in the usual way. You can create files, you can generate data, whatever. But then the container, it's a different entity from the image. When you are done with the container, you can delete it, and the image will be there still and modified for you. So with that, I think the best is to give the floor to Mohammad so he can start explaining the Docker part, and then I will come back later for the Singularity. So I stop sharing, and if you want to take over, Mohammad.
Sorry, I forgot to unmute myself. Do you see my screen?
Yeah, perfect.
Yeah, that's
okay. Okay, great. So thank you very much, Angel, for the great introduction. So let's get hands-on and actually follow up on what Angel was explaining. So let me just explain the problem in practice, right? So for example, you have, your research, your paper depends on some software, right? So for example, let's say you depend on AST Noise Chisel, which is part of the GNU Astro programs that we presented in the third SMAC, 10 SMACs ago. We're already building up a good library of videos. So for example, assume your software, your program, your research, your research paper depends on this program. So like for example, over here, I can just run AST Noise Chisel version and it runs nicely on my computer. Now I want to go to another computer. So when I want to go to another computer and I want to run it, for example, on the IAC servers, for example, or run it on a large HPC or somewhere, you see, like this version here, my results will depend on this version. So if the HPC has another version of this software, my results are going to change. So one solution that may come to your mind immediately is that, well, this program is just a file, right? So look, like we can actually, in the Unix operating system, we can just say which and then the name of the program. And when we run this, look, it shows me, look, this file is here. right? So I can just, for example, copy this file onto a USB stick, in theory, and take it to the other computer, or just post it, put it somewhere else. And on this computer, this is going to work. So look, if I do cp user local bin ast noise chisel, and then I copy it here. Look, now it came here. Look, this is the file. And if I actually run this script, again, it's going to work, right? So on my computer, this works. I can just copy this, the binary, the software's file, and just move it around. But if I move to another computer, things are going to get complicated. And why is that? Because on another computer, the dependencies of this binary are different. So let's have a look at the dependencies of this binary. So look, if we do LDD on the GNU Linux operating system, shows the libraries that a program depends on. So if I do LDD, okay, where was it? Which AST noise chisel? Okay, so it's here. Now I can do, now I'll just run this, okay, user local bin AST noise chisel. Look, all of these libraries, these are the libraries that this program that I use in my paper depends on. Look, like, lib WCS for fitting the RA-DEC 2 pixel coordinates, or libcfits.io to read fits images. Look, and this, so this program, since it was built on my computer, look, it assumes that like libcfits.io is in this location of the operating system. So it works when I just move the file on my computer. But if I move the file to another computer, most probably one of these dependencies is either going to be a different version, or it's going to be a different place in the computer, and it's just going to be a nightmare to run it. And I'm sure you've hit problems before that it says like missing this version of that library or something. So the whole purpose of this discussion is to create an environment. So when we say environment, we mean this. We mean all of these dependency libraries, to be able to just pick up what you have on your computer and run it on another computer. So that's the overall purpose for in practice, following what Angel nicely explained. So let's see how we can do that. So in practice, as Angel was saying, one of the most common solutions is virtual machines. And for example, over here, I'll just run a simple Debian virtual machine for you, so you see what it, for those that may not know virtual machines, let's show it in practice. So look, I'm actually running an Arch Linux on my computer that you're seeing right now, my desktop. My main computer is Arch GNU Linux. However, I want to open now a Debian operating system. So look, over here, I press start, and look, the virtual machine is going to boot. It's actually, look, it's literally booting. Look, this is exactly the menu you see. Look over here, when you boot your operating system, when you turn on your laptop, for example, or your computer, look, it's actually booting. Look, the whole operating system is loading up. It's actually creating a completely new operating system inside a window of my existing operating system. So look, have a look, you see. It's actually a window. Look, I have my own operating system in front of me, and I have the virtual machine here. And then I just like press enter here and go into my account, and boom, look, the whole virtual machine just loaded up. Look, it's a whole operating system, a whole independent graphic user interface. I can open Firefox here. I can, it's a completely parallel operating system. Exactly, if you remember the diagram that Angel was showing before, this is that operating system layer. And look down here, you see, like, look, it has its own virtual disk, it has its own virtual CPU. I can tell it to, only use like this much of my RAM, my computer's RAM, like, 5 gigabytes of my computer's RAM and not anymore. I can tell it to use this many CPU threads. And because it's a whole operating system, this is exactly what Angel was saying. It adds overweight, so it's overhead. So look, like opening Firefox is slower here than when I open it on my own computer, because it has to go through this extra operating system that came in between my hardware and this second operating system that's loading in. So containers are a way to skip this full extra operating system that needs to be booted every time you want to come. So let's turn off. Look, turning off, this is just like your own computer. You come here, you turn off, and it just goes off. Look, it went off. But the good thing with a virtual machine is that, as with Docker containers, you can just pick up this file. Look, you can just clone it. You can just copy it into another file and go to another computer and load exactly the same virtual machine. But well, this has many problems because the virtual machine depends on root. It needs many graphic user interface mostly, and so many technical problems. So now let's get to the main solutions. Now that we understand the problem in practice, also, so one of the solutions to avoid all the overhead and the extra things of a full operating system, I just want to run my software. I just want to run this software, for example. I don't want a whole graphic environment I'm happy with my own graphic environment, for example. So I don't need all that extra overhead. So Docker is one solution, as Ankhel explained. So now Docker is not perfect, right? So there is several problems to it. In particular, so this is the lecture notes that I'll be following here, and you can always have later also. So the main problem with Docker is that it needs root permissions. And this is a huge problem. So I can't run it. Look, if I do Docker image list as a user, look, it says, sorry, I can't. I don't have permissions to actually run. So it needs root permissions, and this is something you don't have on the IAC large computers, for example. They're not going to give you root permissions because you can suddenly mess up the whole operating system. So this is one problem with Docker. It's good when you have root permissions. So you can, for example, I become root here, and now that I'm root, I can run Docker, like a Docker command, and okay, you see, it's actually able to run the command and make sure that I have no images on my computer right now. Okay, so but still, it's very commonly used, and many systems, what they do is that they create a virtual machine on the server for you, and then within that virtual machine, you have root permissions. So you can't mess up the whole server system, for example, but within that closed container, you have root permissions, and then many servers allow you to do this, and you can use Docker images in those scenarios. And in the software world, it's also really used these days, and it's a really big buzzword, Docker, for example, which is really fashionable these days. So it's good to understand the concepts and the limitations and everything. Okay, so we became root. Now let's actually get started and create our environment. So now that you become root, so the first thing you usually have to do, unless you've set your operating system to start, is to activate Docker. So to start Docker, you have to say systemctl start Docker, right? Now I've already started. You can also stop it here. You can say stop, and like this will actually stop the the Docker daemon, because Docker is something that runs in the background. It's always running. The moment you start it, it starts running, and it continues running until you stop it. So for example, on my computer, when I don't need it, I stop it. But then I can always start it like this, because it just takes CPU, and I don't want it. and it's root, so it's a dangerous thing to have active all the time. So even on your own computer. Okay, so you start Docker like this. So now the daemon is running in the background. So this Docker daemon is running in the background, and I can always activate it when I want to. So I just activated it. Okay, so now let's make our first Docker image. So what you do is that, so Docker tries to keep the environment, right? So the best way is to it works through a Docker file. Okay, so let's go and practice. So first, let's make an empty directory, mkdir, like my Docker. Okay, now we made my Docker. I've also put this here, as you can see, every file that I create. Now I go into, okay, so you can also do this without root permission. So sorry, I should have deleted my Docker, and then you can, in fact, it's better to do this without root. So then you come here and you say mkdir my Docker, and then inside my Docker, you would say, so now we're inside the my Docker folder or directory. Okay, now you can actually make a plain text file which defines the Docker file, right? So the plain text file, we'll just start with a very, very basic thing. Emacs, so Emacs is just a text editor. You can use Vim, you can use Nano, you can use whatever you like. Docker file. So this name is a standard file. Now I'll just put NW so Emacs opens inside my command line. Okay, and now this is like the plain text editor. The file didn't exist, so Emacs just created it. And then I'm just going to copy this line. So look, I'm going to tell Docker to install Debian, the same operating system I just loaded in my virtual machine, and I'm going to install the stable slim version. This is the minimal Debian operating system, which only has the very bare minimal set of files that an operating system needs. So we'll just save this and close it. So now if I do cat Docker file, you can actually see the contents. This is all the file has inside of it. So now, and you see the file was actually created here as well. Okay, now we want to build. So now to build so now we need to become root again. And now that we're root, we actually say Docker build, and then from the current directory. So you can like specify a special file, but just like make, which we will introduce in the later snack, Docker file, make has a make file, Docker has a Docker file. You can define so look, when I press this, now it's actually starting. Look, it's all going to the server and it's pulling from library Debian. Look, it's downloading a 31 megabyte file and finished. It downloaded the file, and you can see that successfully built an image with this hash. So now we can actually do Docker image list. Remember before it was empty, Docker image list, and here now look, now we have Debian stable slim, and so this is actually the same image ID that you see here, and this image ID, so this image was created on the server, not on my computer. So on the server that this image got from, so 7 days ago, right? So this actually shows you a very important point in terms of reproducibility. Look, we said Docker stable slim, right? So like 7 days ago on the Debian server, they updated their system, like someone found a bug or something was improved. So they updated the thing on their server. But so like if I had run this 7 days ago, I would have got a different hash, a different minor differences in the operating system. So we have this in mind. It's good, but not exact. Some things get updated all the time. Okay, then so now we have the image, but look, I'm still in my own computer. If I do which AST noise chisel again, I'm still on my own computer. I'm not inside the Docker container yet. Okay, now let's run the Docker container. So to run the Docker container, you would do Docker run -i, which means interactive, because you can remove this -i and it will only run the Docker file and stop. So this is good for automatic things when you just want a pre-defined set of steps to run and finish without you doing any interaction. But to better understand, we'll go with some interaction. And then we'll say -t, which actually means the tag of the image we want to run. So then we say Debian and then stable slim. And when I press enter, look, now you see, even the prompt changed. Look, before this is like how I defined my prompt in my computer. But now look, the prompt is different. It actually says root at this hash. And this actually shows that now I'm in the Docker image. I'm not in my computer anymore. So if you don't believe me, let's do which AST noise chisel. And look, nothing. It doesn't exist. It doesn't exist on this operating system. I'm not in my host operating system anymore. If I do AST noise chisel version, look, it says command not found, because now I'm fully in the Docker container. I'm not in my host operating system anymore. So effectively, this layer that Angel also showed directly talks to the kernel, which controls the electronics of my hardware directly. So it effectively completely bypasses my own operating system, and so it's able to, without all the overhead of virtual machines and things like that, and all the extra graphic environment, I just have a command line access to a fully independent environment that I can just copy on the file and, for example, take to another computer. Okay, so now we're inside the Docker file. So look, if I even do an ls or a pwd, you see I'm in the root of the Docker system, which is a Debian system I set up here. You can set up Ubuntu, you can set up Fedora, any GNU Linux, even non-GNU Linux, you can even set like BSD or any other free operating system. So yeah, as Angel said, you can't load Windows in this, but you can load a GNU Linux operating system in a Windows computer through Docker. So that's good. This is another useful case scenario. So like you have a Windows and like you're in a friend's home and they have Windows and you want to run something on your from your GNU Linux, you can just set up a Docker environment and run your command there. It's going to be a fully Linux operating system that talks directly to the hardware. Okay, so now okay, so now when we want to, so say for example we do our analysis and things, and then when you want to come back to your computer, you just press exit and it's closed. So now we came out of the Docker image and we're back into my computer, for example, and I'll just do a reset to have a clean terminal. So you see now if I everything came back to normal and the Docker file is effectively, the Docker container is closed. Okay, so now let's run it again, and let's have a look just as another example to show you how it's different. So look, let's have a look in user bin. Like this is the place that most software are installed, you know, like ls, cp, I don't know, all the commands that you usually run on the command line, they're here. So okay, and now let's count how many software there actually is here. So look, there's 201 software in the Docker system. Now if I come out and I do the same ls user bin pipet to wc -l, look on my computer, because well, this is my my main computer, so I have like 4,017 software in my user bin directory. So this is like because I've set up my research things and everything. It's my whole operating system software is now here. So now if I load the Docker again, you'll see something interesting. Look, you see this hash? It's different than before. Remember? So if I come up here, look, like before when I went into Docker, this hash was 307BCA to I don't know, something. So you see this hash here? It's different from this one. And this is again what Angel was explaining. The image file that I downloaded when I built my Docker image is a static thing. It's just on the computer. It's a block. It's just static. Every time I run the Docker image, it creates a new container. So let's go into a new terminal and let me show you. So I'll have to come here. Okay. So now in the new terminal, I will make it larger to be visible. And now we can actually become root again. And then I would say sudo. So then I would say Docker container list. Okay, look, now you see, this is the same ID that we saw before. Look here, 972B6F. This is again 972B6F. You see, this is the same container. I'm actually seeing it on another terminal. I can actually keep as track. And this is why it needs a daemon to run in the background all the time. It connects multiple terminals. So for example, I can come in a new terminal and I can run a new Docker instance. So I can go to this same directory and my Docker, and then I can run another instance of the Docker run minus. So we can merge the two options, and then we'll say Debian stable slim. And yeah, you see, I forgot to become root. So now if I run this option again, okay, you see, look, now the container list changed. And if I come here and click, so this, and click and do this Docker container list again, you see, now I have two containers on my computer. Look, it actually says this one was created 10 seconds ago. This one was created 2 minutes ago. So look, this is the old one and this is the new one, and you see they're independent. So for example, I can make a file in this one, in this root directory, I can say echo like test, and then I'll just write this into a file called test a.txt. So now look, when I do ls, I'll have text a.txt, and it has my test, it has the file I created here. But look, and now I'm coming into this Docker image, and I do ls. Look, there's no such file. So these are independent instances of the same image, right? They're independent, and this is another good aspect of having containers, because each one will have a completely different even operating system. It's like an image of an operating system that activates, you do something inside it, a ghost of an operating system, and then it gets deleted as soon as you come out. So look, if I exit from this one, now I'm back into my container. Now my operating system. Now when I go back into the container, look, the hash has changed. You see? And now it's 68C47. Before it was 7EE. And if I do ls, look, there's no more test.a.txt. It was destroyed, deleted, because the container was lost. The container, as soon as I left, that ghost of the image, the operating system, evaporated into space. And now when I load the container again, this is great for testing. So when you're testing something, if you suddenly mess up the whole operating system, don't worry, you can just come out and go back in, and everything is back to normal again. Okay, so now let's actually leave this extra image and go back to the previous one. Okay, so now so now we saw this says, okay, so now I have multiple images, for example. So you can also have multiple operating systems. You can have one Ubuntu, one Fedora, one I don't know, FreeBSD. You can have whatever you like, and then so in many scenarios, okay, so let's exit this Docker image as well. Let's run this Docker container list. So you see, now that I left all my Docker containers, there's no more container. You see, they both, because I closed both of them, and now they don't exist on the computer anymore. Okay, but my image still exists. So if I do Docker image list, you see the image is still here, but there's no containers. There's no containers on the computer. Okay, so let's continue with this step here. So one common thing you'll find, because making an image is so easy, sometimes you just want to delete all the images you have, and then clean up your operating system. So one useful command in this case is this docker ps, which actually loads the images, and then you delete them. Look. You list all the images and you delete them. It's the containers, and then with this other command, docker images minus. So this uses each.At to actually get the documents. Look, it actually deleted all the container images that they were in the cache, and the actual images on my computer. So now when I run docker image list again, look, it's empty. So you see how easy it is. You can just build, because look, you have the Docker file. The important thing is this. Because from this Docker file that we created, look, remember, from Debian stable stream, from this we can always recreate, not exactly, as I showed you before, the operating system gets updated in the server, but almost exactly the same operating system. And there are ways to even make that exactly the same operating system. Okay, so now so as time goes on, you'll be creating many images. Right? If you use Docker, you'll be creating many images. So you want to give names that are relevant for you, right? So in this case, let's call it Docker build minus. So with the -t to build, you give it a name. Like let's call it Mohammad Debian, for example, like my Debian, or Mohammad test, for example, or Mohammad Smack 13, for example, right? And just press enter. So Oh yeah, because I'm not in the proper directory. So let's go to, so I'll just keep this one unchanged, and I should go here because I have my Docker file in this directory. Look, my Docker file is here. I should have run that here. So then I just copy the command, and then let's go here. So now look, it actually is going to download again because I deleted everything, right? So it's going to download the 31 megabyte file again and extracting it. And there you go. You have the new thing. But now the good thing is that this time I have an understandable name for it, right? So now I can actually, when I do Docker image list, look, it actually shows me that it downloaded this Debian stable slim one. And this is the image ID. But then it shows this other image that is exactly the same ID, exactly the same hash, so the contents is the same, but now it has a more understandable name, you know, because now your project, you're going to create, you're going to update the Docker image and everything. So now I can actually remember, like if I made for SMAC 13, another one I make a Docker image from my paper, I don't know, on the cosmic web, on another one I make for a paper on like the galaxy circumgalactic environment or things like that. I make different images and I put different names for my images. And yeah, now you can see how, and to run it, now that you have a good name for it, it's much more easier. You don't have to remember like what it was. You just say Docker, so I'll just fix this, Docker run -IT, like Mohammad SMAC 13. And here you go. Now I created a new container over the Mohammad SMAC 13 file. And well, as you saw, so I already showed this part that when you make a file and exit, you lose the file, right? So you already saw that in practice. Now let's see how you can keep the file. So because when you make changes and when the changes are good, you don't want to delete them, right? So let's make a change. Let's make a file. Let's call it, let's make a file again. So we'll say echo like file to keep, you know, and let's put this in a file called keep.txt, right? So now if I do ls, you see compared to before, now we have this keep.txt in the operating system. So, but this time I want to keep this. I don't want to delete it. So what do? I come in this other terminal. This is again, so the container already has to be active, right? I come in this other terminal and I say docker commit, and then the hash of the container I was running. So this Zoom window just came in the way. Okay, so look, now I say docker commit, and then I copy this here, and I put the hash here, look, and then I say docker commit. Okay, now, for example, I want to update my, you know, this name that I had before. So I say again, Mohammad SMAC 13, for example. Okay, you see, for one moment, it froze that container. It made a copy in the image list and kept that file. So now if I run docker image list, okay, now look what happened. Now remember before, the IDs of my Mohammad SMAC 13 and the Debian images were the same, but now they're different. And look, it actually tells me that this one is created 13 seconds ago, right? So you see, I actually created a new image from the container. And now if I exit this, my Docker image and I come back, then I'm going to see that when I do ls, look, keep.txt is here. And now, so when things are good, you can commit. The Docker has actually taken this name from the same concept in Git. You can commit the container into an image and preserve it for the future. And the good thing is that Docker will do this in a multi-layer phase. So it's not going to repeat the same file. So like in this case, when it shows the two are the same size, you don't have two files of 80 megabytes. You have one 80 megabyte file that's being used in both. And then like in this container, you just have that extra plain text file that we created. Yeah, so as we saw before, you can also give the commit a different name. So like if you're happy, if you want to keep your original like name and you want to create a parallel thing, Just like Git, you can make branches of containers. You can make histories, different histories, and go and build them together. So this is just a basic introduction. There's many things you can do. So for example, I'm going to effectively finish around here because we have a limited time. But for example, let me show you a little more complex Docker file. So look, for example, in this one, I'm saying from Debian stable slim, just like before. Look, in the same Docker build, it's actually going to get, it's going to actually download the, use apt-get to install, for example, GCC, which is the C compiler, and wget, for example. And then with the same Docker build, and then it's going to run, so it's going to make a user, and then it's going to go into the user, because like in the image, for example, in this scenario, I don't want to be root. And then it's going to make a directory, it's going to make the software, it's going to copy, look, some files, the source of my project from my computer onto the directory within the Docker operating system. It's going to copy another one. It's going to copy another one, like my software and my data. This is the software source code. And then it's going to actually run the project. So look, this is the case when I said that you can do this non-interactively in batch mode. So you see, you can do this and then create the Docker image non-interactively and do the job and then even close it. And then you can run a similar command to copy the final product back into your computer, for example, the opposite to what you have here. And there's many things you can do. So for example, you can let's see, you can preserve, this is the commit that I showed before. This is how you can copy files into an existing container that's already open. And then you can even, this is really interesting, you can mount your own operating system file system, a special file in your own operating system within the Docker image. So then every time you go in a directory in the Docker image, you're actually writing files in your host computer. And there's also easy steps to copy the whole. You see, Docker save will actually save the whole Docker image into a tar file that then you can move to another computer. Okay, so this was just a basic introduction, a hands-on basic introduction. Thank you. I'll stop here and give control back to Akhlaghi.
Okay, yeah, so let me share my screen and right, so now the idea is that that I will cover Singularity. So now some of the concepts, we hope that they are clear by now. Singularity is similar in concept to Docker, but it tries to do things differently. So Docker is mainly focused for isolation, while Singularity is more focused to integration. You don't need to run a daemon, so you don't need to, and you don't need to be root. And it's mainly focused on scenarios where you want to run scientific software, and actually is you will find that it's already installed in many supercomputers. Like if you go to La Palma or Mare Nostrum, Peace-Dine, they already have Singularity installed precisely because you don't need to be root. So I'm going to show you just some examples of how to actually build a container and some use cases that I actually use myself regularly. Okay, so for well, you will have this slide somewhere. So in order not to go too long, I will skip some of the links, etc. So I will just show you the commands. So for example, the most simple thing that you can do is similar to what Mohammad was showing. So you can just run, let me just run it in another, in a terminal. So if you run, for example, like this, Singularity run, and then you give the URL of this container, this image. So you can actually, well, this one was very fast because the image is already cached. Okay, I did it before, but the first time it will just download the image. Now it's saying that use this as using a cache image, and you can run some silly program just for demonstration. Okay, so this one is actually just running sort of a fortune teller, so it's giving a different message every time, and then it's asking a cow to say it. Okay, and so now this is the command. So you are running. as I said, you don't have a daemon here, and you can see that I'm running as my regular username. And in this case, what it's just doing is just downloading the image somewhere and running it. But I don't have, in the case of Singularity, the image is just one file. And in this case, if I actually look in the directory, I don't have any files because I'm actually asking Singularity to run directly from the library itself, from the registry. Okay. This will, well, actually, you see that it's using a cache image, and the cache is stored somewhere here, but a cache is just like a regular cache. You can delete it. I mean, it's just to save time, but it's no daemon. So in regular, when you normally use Singularity, you are actually running a container in the directory, but just like a regular program. I mean, you can store it anywhere you want. So in this case, I'm going to store all the containers here in the temp directory. But at this moment, as you can see, there is no container in here. So actually, if you want to download it, you can just use the same command, but instead of run, just do pull. Okay, so I can just pull the container, which actually will take it from the registry and will put it in the directory. So you can see here now there is this is for Singularity file. So this is the whole container. Okay, and it's in my directory. And now what I can do is just run this container, just Singularity run, and I will explain you now what that means. Okay, now it's taking now it's running actually from the container inside this directory. And what it means by running, I will explain later. Okay, but it's basically it's running a predefined script that we will see later how to define it. Okay, and the good thing about Singularity as well is that you can also use different registries. So for example, you can pull directly from Docker containers. So in this case, for example, I'm using the Docker whale-say container, the whale-say image, and I can actually pull it, and it's actually downloading all the stuff, converting it to the Singularity format. And after it's done, you see here that it's creating the Singularity file. And now I should have another image here. Okay. And actually, if I want to run it, now it's a Singularity file. So if I want to run it, I can just run it as before, as for the Singularity container that I got from the other library. And so I can just run it like that. Singularity run whale-say latest, and I ask for the container to run this command, cow-say holy whale. Okay, forget about these warnings. We could fix this, but this is just due to the locale of the container itself. But actually, I'm actually using the container that I downloaded from Docker itself, from Docker Hub, and I convert it to Singularity, and I can use it. So that can be useful because Docker is more mature technology and more well known. So there are many more containers in Docker Hub than in the Singularity registry. So you can take from Docker Hub and transform it to Singularity. So so basically, there are three ways to use a container. Now that we have downloaded one, the one that is very useful is the Singularity shell. Okay, as you see here. So that will basically, if I clear here, you see that, well, I have the two containers here. And if I do shell, basically that will open a shell inside that container. So actually, similar to what Mohammad did, I can, for example, now check for what is the OS release of this container. I can see now that it's Ubuntu 16.04. Actually, if I exit and I do the same in my machine, you see that it's completely different. It's an Arch Linux system. So when I do this, I'm actually running a different operating system on top of Arch Linux. Okay, and the difference with Docker and Singularity, as well, one of the differences that, as I said, is meant for integration rather than isolation. So by default, the whole home directory is shared automatically inside the container. So for example, if I do ls here, I can see exactly the same. If you see, this was outside the container and I had these two files. Now inside the container, by default, I'm still in the same directory and I have the same two files. Actually, I can look at my complete home directory and it's the same as it's my home directory because it's mounted from the host system to the guest operating system. So that simplifies many workflows sometimes. Okay, and yeah, we have access to all the stuff in the home directory and actually a temp directory as well. But also, like with Docker, you can later modify this and decide that you want to mount some other directories if you have code, if you have other code in other places, not in your home directory, etc. Okay, and actually by default everything is shared. So for example, if I do here, what is my host name? So this is CLAdon, and it's the same as my regular one. So many things are shared by default, okay? Because the idea is that you integrate. It's just like a container, but you don't want to isolate completely. You want to integrate with your own operating system, with your host operating system. And so that's, well, what the shell does. You get inside the container and then you can inspect what's inside. Another different way is to use exec. So for example, if I want to run something inside the container, I can just do Singularity exec. So what this does is just run a particular command inside the container. So in this case, I want to run the command fortune. Fortune is this sort of fortune teller or fortune cookie, or I don't know how you call it, but just will give you some random sentence, okay? And that's the way to run a command. And one of the good things that make it easier to integrate with your own host operating system is that you can run, for example, things like pipes. So for example, let me show you here. If you can, for example, just pipe all this output. You see that the output of this command is just some sort of random sentence. So I can just run WC to count how many words and letters are there in this sentence. And it's important to note here that this first part is happening inside the container because I'm running this command with the container. And the pipe is actually being piped to my host operating system. Okay, so I'm mixing very easily a command inside the container with a command outside. For example, I can also do, as I have it here, the fortune command will generate that random sentence, and then cow say is a silly command to actually have a cow say that command. I can see what happens if I try to pipe that sentence to the cow say command. It will actually tell me that cow say is not installed because I don't have that command in my machine. Okay, because so you can see that this part is happening at my host operating system. If I want to run the whole thing inside the container, I can also do it, but then I will have to do something like sh-c. So this is running a shell, and then the command that I want to run is fortune pipe it to cause. So this is, it's only one command that I'm trying to run inside the container, and the command itself is the fortune pipe to cause. So if I do it like that, then it should work, no problem. Okay, and in this case, both things are running inside the container because cause is installed inside. So that's another way to run to use the container. The first one was to get a shell inside, then you have the exec to run a particular command, and then the last one is to use run, and that run will run a predefined script. So for example, if instead of running exec, I just do if I just do run instead of exec, this will run 3 commands, pipe to from one to the other. So it will run a fortune to get a silly sentence, then causate to have the causate, and lolcat to give these colors. Okay, so it's somewhere stored in the script itself. These three commands together. So the description that I want to run these three commands together when I use run, and this is nice because we have this predefined script. We can just treat it as a regular command, so as a regular executable file. Instead of having to type Singularity run, I can just do like if it was a regular executable file, I can just do like that, and it will run exactly the same. Okay, so in case you have your container prepared to run whatever you need with a predefined script, then you just use it as a regular executable file, and you can actually even forget that you're running Singularity. Okay, so for example, I know that if instead of CIF, I call it lolcow latest and forget about CIF, I would even forget that it's a Singularity container. Okay, and I could just run like this, and then the output pipe it to some other commands or whatever. Now, so then we need to learn how you specify these predefined scripts and how you generate the actual container. Okay, so one useful thing is to actually inspect the container. So you can you have the container. If you download it from somewhere, or I give you a container and you want to see how it was created, etc. So you can use the inspect command. So for example, if you want to check what is this predefined script that I was telling you, so you can do Singularity inspect and then tell me what is the run script. Run script is whatever it will run as a predefined script. So when I do this, it will tell me, okay, this is what I will run every time you just do a Singularity run, or when you do like this, or when you run it as an executable file. Okay, so then you can see that. Another useful thing, for example, is that you can check the definition file, what we were calling a Docker file for Docker. So for Singularity file, it's called a definition file or Singularity definition file or whatever. So you can actually check how the container was created. So I can do this for this silly container, and it will tell me something like this. So the syntax is different to a Docker file, but the idea is similar. So you have here I'm saying that I created this container from Ubuntu image. Then I specify what is the run script. Then I specify how it was created. Okay, so actually I was using apt-get update. I was installing all this software, etc. And for example, I'm also changing the environment here. I can change environment variables, so I don't have the problem that I was having with the locals before in the Docker image. So I can do things like that. Okay, so that's useful stuff to check inside a container. And so if you want to build a container, actually you just need a definition file, and you will run something like this, sudo singularity build, and you will give the definition file, and then you will create a Singularity file. For creating the container, you need to be root. That's the only moment when you need to be root, because the idea of Singularity is that you don't escalate privileges. So if you want to be root inside the container, you have to be root outside. If you run outside the container as a regular user, you are a regular user inside the container. When you want to create the container, obviously you need to be root, because you are going to put stuff in user bean and in other places that need root access. So in that case, you need to be root. So the idea with Singularity is that you need access to a machine where you can be root. So for example, your laptop or whatever, you will create the container, and then later you can move this to a supercomputer, for example, and in that supercomputer, you don't need root privileges. You can be a regular user, and to run the container, it's okay. You don't need to be root. But at some point, when you want to build the container, you will need to have root permissions. So, for example, a way to create a new container would be something like this. I explain you now what we're doing. So if I do this Singularity inspect, oops, sorry. If I do this, this will give me the definition file, as I said before. So if I send that to a file, I can save that definition file, and then, oops, sorry. And then just to create a new container, I would have to do Singularity build and then give that definition file and then create a new container. Obviously, if I do like this, I'm changing nothing. But the idea is that maybe you get the definition file, but then you want to modify it, you want to add some other software, and then you modify this definition file to install that new software, and then you will create a new container that will have everything that was in the original container plus whatever you added to the definition file. Okay, so I will skip this one, but that's what it will do. So actually, what I had here is the common workflow on how you will create a container. I will go through this quickly, but the idea is basically that getting a definition file right from the just by writing the definition file is not going, I mean, it's going to be difficult because you don't know exactly what dependencies you have, etc. So the idea, what you do is normally this. So you will create a writable container. So instead of starting with image that is immutable, you start by creating a writable one with an option that is called Sandbox. So that will create a directory instead of a single file. Then you shell into the container, so you get inside, and you use the option Writable. So with that, basically you can do whatever changes you want inside the container. So in here, you get a shell in the container, and then you start installing software, modifying environment variables, whatever you want to, whatever you need to do to get your software and your application running properly. And then as you go, you will record the changes in the definition file. So you have a definition file, and you find that you need to install some dependencies because otherwise your software will not work. So you make those changes and you write them in the definition file. And then if at some point something breaks, it's okay because you have the definition file that you are writing, and then you can always delete the previous container and then recreate it. Then you basically go through this as many times as you need until you get something that it works okay. And then at that point, you can delete the directory, the writable container, and then you create the container from the final definition file as a read-only Singularity image. And then at that point, you have a full container as you wish, with all the applications that you want and something that is repeatable. So I want quickly now to go through 4 cases, well, actually 3, but of things that I do in a regular way. Okay. The first one actually it's a live demo. We don't have time to go through all of it, but if you want, this will be in the slide, so you can actually check how I did it. So the idea is that try to replicate, for example, this lolcow container, but with a different distribution using Ubuntu 21 instead of Ubuntu 16. Okay, so I uploaded the video here to YouTube, and that basically demonstrates this workflow. Let me just show you how it looks, but I will go very quickly through this. So I will start with something like this. This is my definition file on the left. So I would start just by saying that I want to use Ubuntu distribution. And then on the right here is my cell. So I will just start by doing creating a sandbox. So this is just a writable container. So at this point, I will have a container, but that is just a directory. Actually, I can do ls lol smack, and I will see the directory itself. Then the idea is that I will do a Singularity shell. So I get inside the shell, and then I try to install software. Yeah, well, I can see that I'm running Ubuntu 21. I can try to install something, and then as you see, it tells me it's a read-only file system. I get a lot of errors. That's because I forgot to start as a shell writable, okay? Because normally images are immutable, so you have to specify that I want a writable image. So I get inside now, and I can actually modify things. So I can install, now it's okay, I can update the Ubuntu system, I can install things. And then as you can see, as I tinker with the system, I can update the definition file. I know that at first I have to do an apt-get update. Then basically, if you look at the video, then I try to install Caussay. It tells me that I cannot do it, etc. So I find which repositories I have to add. I will skip this, but then I tinker inside the shell, and then at some point I find exactly what I have to do. Then I modify the definition file to add all those things. And then I keep playing with the singular, with the, oops, something died. Let me see. No, sorry, it was not in there. No, it didn't die. So for some reason, it went to another window. Okay, but the idea is that I will just keep on playing with the container, and I will just keep adding things to the definition file. And then the important thing is basically at the end. So at some point, when I'm happy with everything, then what I will do is, as you can see here, remove the whole. Okay, it's doing it again. Remove the directory, the one that was writable, and then recreate the container, but this time just removing the sandbox. So it will, now that I have a proper definition file, it will create the Singularity file, the container in just one single file. Okay, and so that's normally how you will actually do a day-to-day playing with the container. Okay, because you cannot get this definition file right the first time. So you get inside the shell, you tinker with the system itself until you get this definition file. And then this, if you keep this definition file somewhere, this guarantees that later you can rebuild the container in the same way. So that's, well, in this case, for example, this is what I would do. For example, if the lolcow was an application that I developed and I want to test that it works okay in another distribution, this is the way I could do it. Okay, so then I know that it works, but I know that I have to do some extra things, extra dependencies that didn't happen in Ubuntu 16, for example. So I can try quickly the application with many distributions. So the second use case, I skipped this one because this is similar to what Mohammad was saying. Okay, so you can also create a container for reproducibility. So you can put code plus data in the container itself, or perhaps only code. So, and then you use the data in your host operating system. But the idea is that you want to have an environment where you have exactly the same application and libraries. The third one, this is actually something that I use almost daily in my workstation. For example, with Singularity, graphical applications, where you can install graphical applications. And this saves a lot of time in my case, because this, I don't know if you use any of these applications, they are complicated to install, many dependencies, etc. So what I did at some point was to generate a container based on Ubuntu Ubuntu 21, and then I install those codes in that container. It's easy because Ubuntu is so common that these developers here sometimes provide a binary file or a very easy way to install it, much easier than in my actual system. So I install it in Ubuntu, and then I can use it in my host system. So for example, just to give you an idea, this is my machine, and if I do, for example, which this code visit, basically this tells me that it's installed somewhere down there. If I actually look at the, oh, sorry, maybe this is small, maybe make it a bit bigger. So if I actually look at the visit file, it's actually a script, and you can see that it's running Singularity container. Okay, let's not bother about all the options, but basically it's running a container, and it's using some, but I can pass the arguments, etc. But whenever I do visit, it will just run the application, and I can basically forget that this was running inside a container. Actually, I put myself a reminder here, so when I run this, it will tell me running Singularity, so I remember that it's running inside a Singularity container, but I could actually forget. Okay, so and I created this container based on Ubuntu, and in one container I installed all those applications that I was listing there. So for example, I can have Singularity, Mayavi, whatever, and they are all running inside the same container. Okay, and that way I forget about all the difficulties that come with installing graphical applications in my system. Another useful thing that I use from time to time is to actually Singularity merges quite nicely with MPI and with job schedulers like Slurm, for example. So in this case, I was running an example. I wanted to try in La Palma, and I created a container in my workstation, and I installed a particular version of GCC. I installed OpenMPI, I installed the HDF5 library, and also our code Porta, and I can run it in La Palma very easily. Okay, so actually, as I wrote here, the performance in this case was even better than when I installed it natively in La Palma, and probably just due to that because I had a more recent GCC compiler inside the container. And if you see here, for example, so I have it. This is a directory in La Palma, and so you can see here the container itself. Okay, actually using what we saw before, I can check, for example, Singularity inspect the def file. I can see how this container was created. Oh, sorry, Singularity. So look what happens. Inspect def file. So you can see how it was created. So I'm not go through it, but basically I install actually a particular version of OpenMPI, a particular version of HDF5, whatever I need. And if you want to see, for example, how I submit this to the supercomputer, I can see this submit script. So if those of you that use a supercomputer will see that it's actually quite simple. It's this regular Slurm script. The only thing is that now when I specify my executable, I just put Singularity exec. I had to put a number of options, but then I just run my code with the option that I need for my code. But basically, Singularity mixes quite well with Slurm, no problem. I just run as run, and it will use the particular MPI and HDF5 libraries and the particular GCC and everything that I have inside the container. Okay, so this is actually quite useful as well. If you have one code that has a lot of dependencies and you want to run it in another computer, then you can in another supercomputer. Maybe this is an easier way that trying to find exactly which libraries, etc., you need in that particular machine. And with that, those are my use cases. So very quickly through this. So the Singularity Summary, I think the strengths are that it's easy to learn, and it's installed in many HPC systems. You can convert Docker images to Singularity. And the weaknesses is that it's younger and less mature than Docker, and perhaps mainly the main problem at this point is that it's actually actively developed. And so that's good for one side, but maybe actually sometimes you need to keep up with the changes. Okay. And so, and the really last one, difference between Docker and Singularity, the main ones is that Docker is mainly suited for microservices like a web server, MySQL, whatever. You need to have a daemon running and you need root privileges, and it's basically designed for isolation. And Singularity, on the other hand, is mainly focused to mobility of compute in scientific applications. It's very good for running with HPC systems, so it mixes nicely with the schedulers, MPI libraries, etc. And you don't need to have a daemon, or you don't need root privileges. Okay, so I think that's, yeah, that was my last slide. Sorry that we went a bit longer than anticipated, but I hope it was useful. And I think now if there is any questions, I think we can stop sharing the screen, and if anybody has any questions for Mohammad or for myself, you're welcome.
Yeah, you can type your questions on the chat, or just say that you want to ask a question yourself. Thanks a lot, both Mohammad and Angel. I think you really covered a lot of ground today. It's amazing how powerful these tools can be.
I mean, this I understand that probably if you never use it, maybe it's confusing at the first time how you use it. But actually, if you follow these guidelines, or actually the tutorials that are in Docker and Singularity, it's quite easy to get a hand of it. Once you have built one container, then the rest are actually quite easy. So I think the idea of today's talk was mainly to actually focus on what sort of things you can do and when it's useful. The details, like any other tool, maybe you only understand them after you have tried them on your own.
Yeah, I agree.
Exactly. Yeah.
I don't see any questions.
There is one, I think.
Yeah, I have one. I can just say it. These two tools, particularly Singularity, are not available in the normal IC computers, the ones that are connected and are part of the same farm, right? Because it will be very useful to have particularly Singularity available, so that we don't have to be tied to a particular version of Ubuntu or whatever GAO is using for the computers.
Yeah, I mean, Singularity itself, it's easy to compile it yourself, but definitely I think it would be, in my opinion, I mean, I think it would be nice to have also the Singularity, especially because you don't need to be root. So if we could have Singularity installed in the workstations, at least in the bureaus, perhaps, it would be nice, because then you could install your application in your laptop and then just move it to the bureaus and make sure that, I mean, just run it there without having to compile it there, because probably you have different libraries and everything between your laptop and the bureaus. So we can ask for it.
Should be no problem. Oh, there is another question here. Andreu, you want to formulate the question yourself?
Hi. Yes. Thanks for the talk. I was wondering how the overhead of Singularity compares with Docker, if there is any difference in performance.
That's a good question. I haven't studied it myself or compared them. Angel, have you?
I mean, I have seen numbers in some papers, and basically, Docker has a bit more of overhead, but not much. I mean, I don't know if it depends exactly on maybe some particular scenarios or something, but both of them actually run almost as fast as a native application. Okay, but Docker, I don't know if maybe for very short codes or something, maybe has more slightly higher overhead, because maybe this daemon architecture maybe adds a little bit. So in the paper that I saw, basically Docker had more, but not by a big, I mean, not negligible, but not something that important either. And actually both of them run very similar in performance as to what you would get as a native compiled application. That's not true of a virtual machine. Obviously, in a virtual machine, you will have a lot of overhead. But in this container technologies, basically you can almost ignore the overhead. I mean, like, for example, in my case, I was a bit surprised, but that was very nice. I mean, when I ran our code in La Palma within the container, the performance was actually better. I didn't show the numbers, not to make this longer, but actually the performance was better. I mean, in that case, obviously, I think it was just because it was compiled with a more modern compiler, so probably managed to get some extra cycles in there. But even if you compile exactly with the same compiler, libraries, etc., you will get very, very similar timing from container or no container application.
Okay, thanks.
I have a question myself for you, Angel. Can Singularity be used also for an isolation from the system?
Yes, I mean, because by default, for example, you share the home directory and the temp directory and etc. But you can modify that as well. So, for example, in also maybe you have code in some other place, so you can say that you want to also bind that, and you can restrict other things. So you can, for example, say that you don't want to share the home directory and stuff. Complete isolation you're never going to get with either with Docker either, because you're also sharing. I mean, the kernel is the same, so it's not a completely different system like in a virtual machine. But you can sort of, I mean, with Docker you can make it more integration, because you can also bind things that by default are not mounted, and in Singularity the other way. It's just that they approach the same problem from different angles, so you can more or less tweak both to behave similar, but the emphasis in one is isolation and in the other one is integration. But you can, if you're interested for some reason, you can make both of them behave more similar. What you're not going to be able to do with Docker, at least as far as I know, is to run without root permission. And so in my scenario, that's a problem. But I mean, depending on what you need it for.
Yeah, exactly. For me too, this is a big problem with Docker.
All right. And I see. Well, I would like to remind everyone that the slides of these talks and the actual tutorials are posted online, right? We don't give the actual URL in every single talk, but I think it's in the first or the second one of the SMACs, and we should start including it in the summaries of the talks. You're muted, Mohammad.
You're muted, Mohammad.
So I just uploaded the URL to the chat for the Docker part, and Angel will later send me the PDF. And in the same repository, we'll have the PDF of all the slides as well, of all the SMACs. So this is the link. Yeah.
Wonderful. Thanks very much. So then we'll leave it here. Thank you everyone for coming, and we'll see you next time in next SMAC.
Okay.
See you.
Thank you.
Bye-bye.
Bye-bye.